Hello friends, this is the another lecture of series solution second order differential equation. In today's lecture we will discuss case second of Frobineous method when the roots of indicial equations are equal. So we are taking one problem solved in series x minus 1 y double dash plus 3x minus 1 y dash plus y equals to 0. So first convert it into the standard equation, that is in the form of d2 y over dx square plus p dy over dx plus q y equals to 0, and on comparing we get p equals to 3x minus 1 upon x into x minus 1 and q is equals to 1 upon x into x minus 1. Now in this problem the initial point is not given, so for this we have to consider initial point as x equals to 0. So first we have to identify whether there is ordinary point exists or singular point exists. So for ordinary point at x equals to 0, p is equals to infinite. So ordinary point does not exist. Now we have to check singular point. So at x equals to 0, xp, which is equals to, when we multiply by x then it will convert into 3x minus 1 upon x minus 1, and when we put x equals to 0 then it will become 1, which is not equals to infinite, and same as x square q. So at x square q it will convert in as x upon x minus 1, and which is equals to 0 and which is also not equals to infinite. So regular singular point exists. So applying Frobineous method, so let its solution be y equals to a naught x raised to power m, a1 x raised to power n plus 1 plus a2 x raised to power n plus 2, an x raised to power m plus n, and so on. Let it is equation number 2. Now find dy over dx and d2y over dx square. So dy over dx is equals to a naught m x raised to power m minus 1 plus a1 m plus 1 x raised to power m plus a2 m plus 2 x raised to power n plus 1 plus an m plus n x raised to power m plus n minus 1, and so on. That it is equation number 3. And on again differentiating it, we get d2y over dx square, which is equals to a naught m minus 1 x raised to power m minus 2 plus a1 m plus 1 m x raised to power m minus 1 plus a2 m plus 2 m plus 1 x raised to power m plus an m plus n m plus n minus 1 x raised to power n plus n minus 2, and so on. Let it is equation number 4. So on putting 2, 3 and 4 in equation number 1 we get, and let it is equation number 5. Now we have to equate to 0 the coefficient of lowest power of x, and from here the lowest power of x is, when we multiply by x square it will be x, when we multiply by x it will be x raised to power m minus 1, from here x raised to power m and x raised to power m minus 1. So the lowest degree of x is m x raised to power m minus 1. Equating to 0 the coefficient of x raised to power m minus 1. So for this, when we multiply by x square, then the coefficient of x raised to power m exists. So leave it. When we multiply by x, then the coefficient of x raised to power m minus 1 is minus a naught m into m minus 1. When we multiply by 3x, then the coefficient of x raised to power minus 1 does not exist. When we multiply by 1, then it will be minus a naught m. And the coefficient of x raised to power m minus 1 is also not exist from this particular condition. So it is equals to 0. But from here, a naught cannot be equals to 0. So m into m minus 1 plus m is equals to 0. So from here on solving, m equals to 0, 0. So roots are equal, and this equation is known as initial equation. So complete solution is y is equals to C1 y at m equals to 0 plus C2 del y over del m at m equals to 0. Let it is equation number 6. Now we have to equate to 0 the coefficient of x raised to power n. Equating to 0 the coefficient of x raised to power n. So the coefficients are, when we multiply by x square, then a naught m minus 1. When we multiply by x, then minus a1 m plus 1 m. When we multiply by 3x, then plus 3 a naught m. When we multiply by 1, then minus a1 m plus 1, and this is a naught equals to 0, and it is equals to a1 m plus 1 whole square equals to a naught m plus 1 whole square, or we can write it as a1 equals to a. Now equating to 0 the coefficient of x raised to power m plus n. So when we multiply by x square, then the coefficient is an m plus n minus 1. When we multiply by x, then this will be the coefficient of m plus n minus 1. So on putting n equals to n plus 1, we will get a n plus 1 m plus n plus 1 m plus n. Same as when we multiply by 3x, then the coefficient is 3an m plus n, and when we multiply by 1, then the next succeeding term is an plus 1 mn plus 1, and from here the coefficient of x raised to power m plus n is an equals to 0. So on solving, we get an plus 1 m plus n plus 1 whole square is equals to an m plus n plus 1 whole square, or an plus 1 equals to a. So this is equation number 7, and this is known as recurrence relation. So from this we have to calculate a2, a3, a4 and so on. Putting n equals to 1, 2, 3 and so on in equation number 7, we get a2 equals to a1, that is a2 is also equals to a naught because a1 is equals to a naught. a3 equals to a2, but a2 is equals to a naught, so a3 is also equals to a naught. Hence from here all the terms, all the a's are equals to a naught. So on putting these in equation number 2, that is putting a1, a2, a3 and so on in equation number 2, we get y equals to a naught x raised to power m plus a naught x raised to power m plus 1 plus a naught x raised to power m plus 2, a naught x raised to power m plus n and so on. Or we can write as y equals to a naught x raised to power m 1 plus x square plus x cube and so on. So this is equation number 8. But this is not the complete solution, because complete solution is occurred by equation number 6. So for this equation number 6, we have to find y at m equals to 0 and del y over del m at m equals to 0. So at m equals to 0, a naught, when we put n equals to 0, then this will become 1. A naught 1 plus x square plus x cube and so on. Let it is first. Now differentiate partially with respect to m. Del y over del m is equals to a naught, and the differentiation of x raised to power m is, we are differentiating with respect to m, so it will work as a raised to power x. So the differentiation of a raised to power x is always a raised to power x log a. So a naught x raised to power m log x, and 1 plus x square plus x cube remains as it is. So del y over del m at m equals to 0 is equals to a naught log x, 1 plus x square plus x cube, and so on. This is second. So on putting first and second in equation number 6, complete solution y is equals to c1 y at n equals to 0 plus c2 del y over del m at n equals to 0. So this y is equals to a naught 1 plus x square plus x cube and so on, plus a naught c1 a naught plus a naught c2 log x 1 plus x square and so on. Or we can write it as a naught c1 plus c2 log x into 1 plus x square plus x cube and so on. So this is the required solution. Hope you understand the content of this particular lecture. If you like this lecture, then like and subscribe my channel. Thank you.